Physical linear time invariant, or LTI, systems produce highly coupled dynamic behaviors. When a multi-axis robot arm moves, multiple motors, joints, and masses interact and react simultaneously. To control these systems, engineers map their physics into mathematical models. In many textbooks, these mapping methods are taught as isolated, separate subjects. The first method is the time domain, tracking system changes second by second using coupled ordinary differential equations. The second operates in the matrix domain, using state space representations to organize variables into arrays. The third is topological, mapping architecture using signal flow graphs. These three domains look mathematically distinct, but they are perfectly interchangeable. We are going to trace one specific mathematical property, the characteristic equation, across all three domains to verify that equivalence. Recognizing how this property bridges the domains allows an engineer to select the best mathematical lens for whatever system architecture they are building. We start by analyzing a physical system using standard time domain calculus. Look at this specific second-order ordinary differential equation. To translate this into an algebraic transfer function, we must assume zero initial conditions. We apply the Laplace transform. This maps the time domain calculus directly into S-domain algebra, converting the derivatives into S variables. Now we can group all of our output terms together to prepare for isolation. Rearranging the equation to isolate the output over the input gives us our formal transfer function, g of s. We can simplify this fraction by dividing out the common factor of 2 across all terms. Notice the polynomial remaining at the bottom of the fraction. This specific denominator is the system's characteristic equation. It defines the core behavior of the system. We can map our derived denominator directly against the standard form of a second-order characteristic equation. By equating the final terms, we extract a natural frequency of 3 radians per second. Equating the middle terms and plugging in that natural frequency gives us a damping ratio, or zeta, of 1. A damping ratio of exactly 1 means the physical system is critically damped. The algebraic denominator has explicitly revealed the physical dynamics. Standard polynomials work well for single inputs and outputs, but as systems scale in complexity, engineers shift to state space representation. State space works by unpacking an nth-order ordinary differential equation into a clean system of multiple first-order differential equations. This visualizes the system matrix, matrix A. It captures the internal dynamics of our state variables. The general formula for deriving a transfer function strictly from these state space matrices looks like this. Look closely at the matrix inverse operation, right in the middle of that formula. A basic rule of linear algebra dictates that computing a matrix inverse requires dividing by its determinant. Because of that required division, the matrix determinant inherently becomes the denominator of the resulting transfer function. When we execute the determinant calculation for our specific matrix A, the matrix math yields s squared plus 6s plus 5. This resulting polynomial is our characteristic equation, generated entirely through linear algebra. Next, we factor this characteristic equation to locate the system poles. Factoring the polynomial reveals roots at -1 and -5. We plot these on the S-plane. Because both poles sit squarely in the left half of the S-plane, the matrix calculation proves the system is stable. State space handles matrices well, but analyzing massive interconnected multi-loop topologies requires a different approach. Attempting to reduce dozens of system blocks algebraically is highly error-prone. To bypass brute force algebra, engineers use a topological algorithm known as Mason's gain formula. This is a signal flow graph. It visually represents system variables as nodes and the multipliers between them as lines with arrows. The first step in Mason's algorithm is to identify the forward paths. Here, we trace a single forward path moving continuously from input to output. Next, we identify the individual closed loops within the topology. We have loop 1 between nodes 2 and 3, and loop 2 spanning nodes 3 to 5. Notice a critical topological property here. These two loops are non-touching because they share no common nodes. Now we use those loops to construct the graph determinant, denoted by the symbol delta. The formula for delta takes 1, subtracts the sum of the individual loops, and adds the product of any non-touching loops. We expand those loop variables, replacing L1 and L2 with their respective gain and feedback terms. Distributing the negative signs cleans up the expression, giving us our final delta. In Mason's formula, this graph determinant, delta, functions as the characteristic equation for the global network. Even though we are working with symbolic variables here, this delta is the exact topological equivalent of the algebraic denominator we derived earlier. We have arrived at the characteristic equation through 3 different mathematical lenses: transfer function algebra, matrix determinants, and topological path tracing. If we were to map the exact same physical system through each of these processes, these 3 distinct operations would arrive at the same identical polynomial. Time, matrix, and graph representations are just different dialects of the same mathematical language. Whether you are factoring polynomials, computing matrix eigenvalues, or tracing topological loops, the core engineering operation is identical. You are always isolating the characteristic equation to hunt down the system's poles. Mastering this representational equivalence gives you the flexibility to choose the most efficient modeling strategy for the physical architecture at hand.